crystal plasticity. With enough activation energy, this is enough force being applied to that crystal, and or enough heat, because temperature makes it easier, dislocations can migrate through the lattice. So if we have a point, a linear or a planar dislocation, it can move. We saw how the point defect, that vacancy, can move. Well, the line defects and the planar defects can also move. And this is caused by a system achieving a lower internal strain. So if that imperfection moving makes the whole object have less strain on it, it relieves stress, then it's going to happen. It may take a long time, it may take only a short period of time, but it's going to happen. So something that will achieve a lower internal strain, and if there's differential stress, so there's more downward pressure than there is from the sides or vice versa, this kind of thing is going to happen. It'll happen in three ways: glide, creep, also known as climb, so it's not two different ways. Creep and climb are the same thing, and twinning. Now, we saw some pictures of pretty twinning. That's not the only kind of twinning that happens. So glide. We start out with a nice regular crystal lattice, and somebody starts pushing really, really hard on the upper half of the left side of our cube here. And we start getting glide happening. The top is compressing where the bottom isn't. And so we have an imperfection. We keep pressing, and eventually the whole thing glides over like that. Now we have a planar defect. And you can see that it doesn't have to happen all at once. It can kind of scissor its way through. And this is, it can either glide as a whole, where in the on the right hand side here, the top half, the front edge of it, moves over completely all at once, and then consecutively each row behind it moves over. Or like on the left, where we're getting this linear dislocation through it, and that linear dislocation moves along until the whole thing has slid over. So glide can happen in both ways, or a combination. Now climb is when you have something like that second one here, so this guy on the right, where it's kind of scissoring across, and then it jumps up a row, so it's not staying in the same plane anymore. Basically what happens is we get a vacancy, so this imperfection that's gliding along, so, there's a vacancy right above or right below it, and that's going to make it jump. It's going to make it climb. So we have this vacancy right next to this line imperfection. So our stressed, our imperfect block or cell within our matrix is going to move upward. It's going to climb. Now twinning. There are two different ways. Oops, sorry. Got extra noises. I'm recording at home tonight. Twins that grow during the growth of the crystal are called growth twins. Those tend to be those really beautiful ones that we saw in that photograph that we like to see. Those make beautiful crystals. Twins that grow in response to stress are mechanical twins. They're usually only noticeable under the microscope. Glide of partial dislocations end up with the crystal lattice in a different orientation are separated by a twin boundary. So if that glide causes the parts on either side of it to be in different orientations, so it doesn't just slide beautifully along, but there's some twisting or bending at the same time, then we end up with a mechanical twin. You can look in your book on page 214, table 9.2, for a review of the crystal systems. So we can have this kind of twinning. This is the growth twins up here at the top. This happened as the crystal was growing. Or we can have mechanical twins. This is stress-based. Sometimes these can also be growth-based, but a lot of times this is mechanical twinning, stress-based, and we can only see it under the microscope in cross-polar light.